So the first question. So we like to find the Taylor series expansion and the radius of convergence around z equal to 0 for the following function. So this function is z by z to the power 4 plus 9. So we would like to find the Taylor series around z equal to 0. So to tackle these kinds of problems, so we begin by noticing whether the given function is analytic or have some singularities or something like that. So let us first examine the points of singularity, if any. So we immediately see that the numerator is entire function, so simply it's z, but the denominator is z to the power 4 plus 9. So it has some zeros, right? So it's a quartic polynomial, so it will have 4 roots. So since the denominator has some roots, it means that the fz is not an entire function, so it will definitely have singularities. So, but we are asked to find the series expansion around the point z equal to 0, and we see easily. So around z equal, so at z equal to 0, the function is analytic. See, at z equals to 0, the denominator doesn't vanish. So z equals to 0 is in the region of analyticity of this function. Okay, so we can just simply use the Taylor series formula. So, and another thing is that since it is analytic at z equal to 0, so there will be no negative powers of z when we will expand around z equal to 0. Because you see, so negative powers in z means, so whenever you put z equal to 0, so that will diverge. So negative power in z in this kind of series expansion is a signature of singularity, so which is not present here at the point z equal to 0. Okay, so the simple function. So I hope you can all follow the mouse pointer. So please follow. So this z by z to the power 4 plus 9. So we can easily write the denominator like this: 1 plus z to the power 4 by 9, 1 to the power minus 1. Okay, and then from there on we just simply use the binomial expansion for negative powers. So pretty straightforward. So this second line is nothing but the binomial expansion applicable for a negative power. So here the negative power is minus 1. And of course you know that this series expansion will be valid when these criteria is satisfied. Like modulus of z to the power 4 by 9 must be less than 1 for this binomial expansion to converge. Then I have just written like the last line is just a simplification, like z to the power 4n plus 1 and 9 is 3 square, so I have just written 3 to the power 2n plus 2. And this criteria for convergence, z to the power 4 by 9 less than 1, it translates into mod z less than root 3. Just, I mean, 1/4 power of 9. So we find that this is the series expansion around z equal to 0, and the radius of convergence is root 3, because this is valid for mod z less than root 3. So this is the answer. So okay, this was the easy problem. So I think in the lectures you have taught that to find this series expansion we need to do the complex contour integrals, right? We have to use the Cauchy integral formula, higher Cauchy integral formulas and all that to find the coefficients. So you can check yourself, if you follow that prescription and find term by term, so all of the terms will match with these individual terms in this series. So we usually do not employ that method because most of the time the series expansion for the function in question is known to us from real analysis or other. Like here, so here it is 1 plus x whole to the power minus 1, and we all know its series expansion in terms of binomial expansion. So here simply we used that concept. So otherwise we are of course free to use the complex contour integral techniques also. So like as you are familiar, so to find the coefficient of the power z to the power n, all we have to do is to integrate this function multiplied by z to the power n minus 1 over the over a contour circling the z equal to 0 point, as has been taught in the lecture. And yeah, you have to divide by 1 by 2 pi I. So that was taught in the lecture, but here you simply know the series and we directly wrote that. So let us now move on to the second problem. So if there is any question, please feel free to ask. If not, then I will move on to the second problem. So the problem. So here we have to find the Taylor series expansion of this given function z divided by z minus 1 into z minus 3. So in the region mod z minus 1 less than 2. So here the region is already given, and we have to find the Taylor expansion applicable in this given region. Okay, so again we examine, we begin by examining the points of singularities of this function. So let us first note that the region is in question. So we recognize that it is the interior of the circle that is centered at z equal to 1 and its radius is 2. So it is only the interior of that circle, but the boundary is excluded. So it is this region. So it's an open domain, so like open state. So now we'll look at the singularities of the function. So no problem with the numerator, but the denominator has 2 zeros. So this is already factorized. So it is. So we quickly take out the zeros. So the zeros are at z equal to 1 and z equal to 3. Okay. And since the powers of these both factors are 1, so these are first order pole singularities. So both z equal to 1 and z equal to 3 are first order poles of this function fj. Now we will see whether this singularities lies inside or outside the given region. So clearly the pole at z equal to 1 lies inside this region, because of course, as I said, and you recognize that the center of the circle is at z equal to 1, so which is of course in the interior of the circle. Okay, so the pole z equal to 1 is inside the region, but you see the other pole at z equal to 3 is just outside the circle, because as I said, the boundary of the circle or the circle itself is not considered as this region. So it is the interior of the circle. Okay, and z equal to 3 lies on the circumference of the circle. So it is at the boundary. So this z equal to 3 point just lies outside the given region. Okay, so in this, so we recognize that the function fz in the given region has a singularity at z equal to 1. And whenever there is this kind of singularities, so we should so here we, since this region is given like that, so centered around this point 1, so we should look to expand this function around this z equal to 1 point. Okay. So yeah, we will look to expand this around z equal to 1. So what does this mean? So this means that we will express the function fz as a power series in the variable z minus 1 instead of z. So when we expand in powers of z only, so that is the power series centered around z equal to 0. But here we will have to find the power series centered around z equal to 1. So that is why we will have a series in z minus 1. So, and as I say, so since z is a pole and hence it is a singularity, so this power series must have negative powers of z minus 1, and that is the signature that this function is singular at z equal to 1. So as I said, so if we put z equal to 1 in that negative power, so you will get immediately an infinite answer. So that is why it is singular at that point. So to do this kind of expansion around a center that is not 0, so that is the usual trick. So let t equal to z minus 1. Yeah. So let t equal to z minus 1. So this is just a change of variable. So mod t less than 2 because the region was z minus 1, mod z minus 1 less than 2. So now we will look to expand. So fz is given by this z divided by z minus 1 into z minus 3. So we will put t here. So z was t plus 1, z minus 1 is t, and z minus 3 is t minus 2. So we simply made this substitution, and then so we see that this can be expressed in sum of two rational functions. So this is just an elementary algebra. So I have just separated out these two terms. So it is easy to check, and then we'll look to expand the power series as in powers of t. So as I said, so already in this step we have this negative power of t. Okay, so t means z minus 1. So this is the negative power of z minus 1. And the second part, 1 minus t by 2 to the power minus 1. So of course it has no singularity at t equal to 0. So look at this term. So this term is analytic at t equal to 0. Okay. So of course again we will use the binomial expansion for negative power, and simply, so this is 1 minus t by 2 to the power minus 1. So its series is t by 2 to the power n, and of course it is valid for mod t by 2 less than 1. So you see, when you put t equal to z minus 1 here, so we recover the given region. So this is equivalent to mod z minus 1 less than 2. So that is precisely the region that was given in the question. Okay. So this is the power series we were after, and then finally we again substitute z in term instead of t, and simply we get this power series. So this is our final answer. So yeah, that was the answer to this question. So yeah, if there is any question, please feel free to ask. I guess not. So let us move on to the third problem of the session. So we are given a power series. We are asked to find the analytic function to which it will converge inside its circle of convergence. So this is the power series we are given. So of course you can immediately recognize that this is the power series of the exponential function, right? So 1 by n factorial. So put this thing inside like x. So 1 by n factorial x to the power n summing over n to the power 0 up to infinity. So this gives e to the power x. But here we will elaborate on the circle of convergence, the convergence criterion, etc. And then after all these considerations, we will write the final answer. Okay, so let's begin. So this is like writing formal answers for mathematics. Like, so the series in question is given. So this is the series in question. So we would first like to find the center of this series expansion. So like around which point it is expanded. So for that purpose, we rewrite this as this. So like you can achieve this state by multiplying the numerator and denominator both with minus I. So you immediately get this. Thus, what do we see now? So we have power series expansion of this form, an z minus 2i whole to the power n, with an, which is this coefficient 1 by n factorial and 1 minus I root 2 to the power n. And this power series is centered around this point z equal to 2y. So again, it is not centered around z equal to 0, but it is centered around z equal to 2y. Okay. So now let us find the radius of convergence. I hope you are all familiar with this formula, the standard formula for this radius of convergence. So how do we find the radius of convergence? So to find the condition of uniform convergence, we mainly employ two kinds of tests, right? So one is the root test and the another is the ratio test. So here we will see that okay, you can also use the root test, but I will mainly use the ratio test because I find it easier to use. So what is the criteria? So this is like, so the series was an z minus 2i whole to the power n. So what is the criteria for uniform convergence? The ratio of the term of a term, like this is the nth term of the summation, right? So the ratio of the n plus 1th term and the nth term must be less than 1. So the absolute value of that ratio must be less than 1 when n going to infinity. So that is the criteria for uniform convergence. So I have simply used that here. So this is the criteria for uniform convergence, and then I have substituted an plus 1 and an and wrote their ratio. So you can immediately recognize the ratio if an is given by this function. So clearly it is this one, n plus 1 by I root. Okay, so the second step, and the third step. So you just invert this thing to take that the other side of the inequality, and you get this. So our mod z minus 2i have to be less than this limit. But what do we see? So this limit tends to infinity in the n tends to infinity limit. So this means that since the right hand side is infinity, this means that the radius of convergence is infinity also. Because you see, whenever mod z minus 2i is less than infinity, the series will uniformly converge. So that means the radius of convergence is infinity. So that in turn means that the power series represents an entire function, which means that this, since the series is convergent for uniformly convergent for any value of z, any finite value of z, so that means the function is analytic for all values of z, and since the function is analytic for all values of z, that means the power series, so that means the function to which this power series will converge will represent an entire function. So yeah, that was the whole logic. So we just derived the radius of convergence to be infinity, and then now we finally sum this series. So this is the this was the series, and as I said in the beginning, so we immediately recognize it to be the exponential function, and yeah, so that is the final answer. So yeah, this is the series, and this was expected because we know that the exponential function is an entire function, so it converges for all values of z. So yeah, that's that. So that was a pretty straightforward problem. So let us now move on to the next problem. Again, so similar kind of problem. So we already did the analysis in the previous problem, so we will just repeat all this analysis here also. So we have to find the circle of convergence of this given series. Okay, so how do we find the circle of convergence? So we find the center around which the expansion is being made, and then we find the radius of convergence. So these are the two things necessary. So we already see from the expansion in question that the center around which this is expanded is z equal to -2. So this is a power series around z equal to -2, and there is no negative power in z. So this is, so in the region in which it is being expanded, so it represents an analytic function in that region. So what is our function? So these are the coefficients. So a n minus 1 is 1 by 4 to the power n plus 1 whole cube. You see, because here this is z plus 2 whole to the power n minus 1. So this is the coefficient of the n minus 1th power, and this is valid for all n greater than 1. So this is the nth coefficient, and again our standard formula for finding the radius of convergence. So I'll again use the ratio test, but you are of course free to use the root test also. So again, so find the ratio of the nth term of this summation and n minus 1th term of this summation, and in the limit n going to infinity, the absolute value of this ratio should be less than 1 for this function to be uniformly convergent. So this leads us to this condition, which implies that, so now I will directly substitute these coefficients, right? So for n minus 1, this is this, and similarly we can easily find the coefficient for an, and if you take that ratio you will get, so this is the ratio an by an minus 1. Okay, and this is the term already that was the summation, and again we'll take this term to the other side of the inequality. So our criteria for uniform convergence is now mod z plus 2 have to be less than this limit. And what do we recognize? So this limit is easily calculated to be 4, right? If n tends to infinity, this limit is, the inside limit is 1 and we have a factor of 4, so this limit is 4. So our criteria for uniform convergence here is mod z plus 2 less than 4. So this gives us the radius of convergence. So our radius of convergence is 4. Okay, and we are already expanding around this point z minus 2. And as we say, so the function is analytic inside this region. So mod z plus 2 less than 4. So the circle of convergence is given by mod z plus 2 is equal to 4. So inside this circle, the function is analytic. So that is why we can expand into the Taylor series with no negative power. And on the boundary of the circle, as we see, our ratio test fails because precisely at the boundary, this ratio is 1, is exactly equal to 1. So precisely at the boundary, our root test fails and we cannot conclude anything about the uniform convergence or about the uniform convergence of this function. So inside this region, this is definitely uniformly convergent, and hence the circle of convergence is mod z plus 2 equal to 4. So okay, that was pretty straightforward. This is the main concept of today. So let us move on to the next one. So again, same problem. So this is, I think this is easier because here we have to just find the radius of convergence. So again, we are given this power series and we have to find the radius of convergence. So again, I will employ the ratio test, taking the ratio of n plus 1th term with nth term and examining that absolute value in the limit n going to infinity. So as we see, so this is the an, so our an is this coefficient, the coefficient given in question. So simply take the ratio and we find out that this an plus 1 by an is given by this ratio inside this modulus and multiplied by half. So clearly again we will take this coefficient onto the other side of the inequality. So for uniform convergence, mod z have to be less than this limit n going to infinity 2 into this function. So of course this is a complex number inside, so we'll have to take its absolute value. So this is the absolute value, see 1 plus n plus 1 to the power 4 and 1 plus n to the power 4 to the power half. So this is the absolute value, and so of course this kind of limits are easy to calculate. So n going to infinity, so you see in the numerator the maximum power of n is n to the power 4 and the coefficient of that term is 1. Similarly, and of course, and you can drop the other terms so that are in less power in n in comparison to n to the power 4 term, because we are looking at this limit n going to infinity. So the numerator is effectively n to the power 4 in the n going to infinity limit. So is the denominator. So you can ignore 1 in comparison to n to the power 4 in the n going to infinity limit, and so we find this limit to be 1. Okay. similarly, so for for more visibility, we can put x equal to 1 by n and convert this limit like x going to 0 plus. So you see, if n is infinity, so x will be 1 by infinity, that means 0, and it's a positive, so it is slightly larger than 0. So that is why I have written x going to 0 plus. And you can substitute n equal to 1 by x all in numerator and denominator, and you will get this thing. And simply put x equal to x going to 0 plus in the numerator and denominator, we will again find, so 0 plus 0 plus 1 whole to the power 4, so which is 1, divided by 1 plus 0 to the power 4, which is 1. So again the inside is 1. So our criteria for uniform convergence is mod z less than 2. So simply the radius of convergence here is 2. So that's that. So all we have to do is to evaluate these limits in n going to infinity limit. So that is all we have to do in these kinds of questions. So yeah, this concludes our discussion on the power series, and now I will move on to two problems that deals with the maximum modulus principle. Okay. So if you have any question on power series, please, I think it's a good point to ask. Well, if not, then we quickly move on to the maximum modulus principle. So yeah, these two problems are much more involved in comparison to the ones that we have just described. So we have to find the maximum modulus of this function z cube minus z plus 2 on the region mod z less than equal to 1. So the region given here is the circle and is the interior of the circle mod z equal to 1 and its boundary. Okay. So what does the maximum modulus principle say? So the maximum modulus principle says that if a function is analytic in a given region, so the maximum value of the modulus of that function occurs on the boundary and not inside the boundary. So it have to occur somewhere on the boundary. And similarly, there is also a minimum modulus principle that says that the minimum value of the modulus also have to occur on the boundary, not in the interior region. Okay, so here we see, so our fz is an entire function, so of course it will be analytic in the given region also. And so by the maximum modulus principle, the maximum of modulus of fz, so fz is analytic in the region. So yeah, so our function is entire, so definitely it is analytic inside the given region. So by the maximum modulus principle, the maximum of this modulus of this function must occur somewhere on the boundary, so which is mod z equal to 1. So the maximum have to occur on the circle, on the unit circle. So from the maximum modulus principle, we can infer that much. So now we will not bother about the interior region. We will only consider the boundary, which is this circle, unit circle. So of course, as we are all familiar, so the unit circle mod z equal to 1 can be parameterized as z equal to e to the power I theta, where theta varies from 0 to 2 pi. And so please look at this inequality. So theta can take the value 0, but not 2 pi, because theta and 2 pi are the same points. So that is how we parameterize z on the unit circle. So now we'll substitute z equal to e to the power I theta in the function. So what do we have? We have e to the power 3I theta minus e to the power I theta plus 2, and now we will write it in the real part and imaginary part. So easily cos 3 theta minus cos theta, which are the real parts of these two functions, plus 2 plus I sin 3 theta minus sin theta, which are the imaginary parts of these two functions. So clearly the modulus is this real part square plus imaginary part square and square root of the whole summation. And now, using various trigonometric identities, this can be simplified in this form. So 1 plus sin squared theta, 1 minus 4 cos theta whole to the power. So think, these are just lengthy trigonometric algebra. So you just have to get your hands dirty, and there is nothing mysterious about this. So all you have to use are these four identities, four trigonometric identities. So like you will have to use 2 and 3 and 4. Okay, and 1 also. So yeah, all these four trigonometric identities will be in use when we simplify this expression into this one. So that's that. So coming back to the conceptual consideration. So the modulus is given by this function. So as a function of theta. So we have to find the maximum of this function. Okay. So root half. So we simply have to find the maximum of this function. 1 plus sin squared theta, 1 minus 4 cos theta. So maximum of this will correspond to maximum of the modulus. Clear? So now it is a problem of real calculus. So you are given a function of a variable theta, and you will have to find the maximum of this function. So simple one variable calculus problem. So how do we do this thing? So we take the derivative of the given function with respect to our variable and equate the first derivative with 0. The roots of that equation gives us the point of extrema, and then we examine the points, we examine the second derivatives at those roots and conclude accordingly whether they are minima or maxima. So let's begin. So our g theta is given by this. So we take the first derivative with respect to theta, and easily that can be found to be this one, first one. Then I have factorized, I have taken a factor of 2 sin theta out. That leaves us with 2 plus cos theta minus 6 cos squared theta. So again you will have to use sin squared theta is equal to 1 minus cos squared theta. If we use that thing, so you will get this second thing, and then I have further factorized the second line. So I have represented this first derivative. Okay, so I have represented this first derivative as a factor. So in its factorized form. So for to find the points of extrema, to find the points of extrema, so as I said, we will have to equate the first derivative to 0, and since we are already in the factorized form, so we see this will give rise to 3 roots. Okay, and these are sin theta equal to 0, cos theta equal to 2 by 3, and cos theta is equal to minus 1. So these are the 3 roots, and there is another way in which you will not have to use the second derivative. So that is that is much more quicker and efficient way. So I'll just use that. So having found these 3 roots, so I'll just substitute those values in our given g theta and compare the 3 values. So among them, whichever will be the maximum will correspond to maxima of the function. So simply, so if we put sin theta equal to 0, so we get g theta equal to 1. So put sin theta equal to 0 here, and you get g theta equal to 1. Simple. And then if we put cos theta is equal to 2 by 3, then you will get g theta to be 2 by 27. So in this function, so what we have to do, cos theta is 2 by 3 and sin squared theta is 1 minus cos squared theta, and then substitute the value of cos theta, and this will give you 2 by 27. Similarly, cos theta is equal to minus half will give us g theta equal to 13 by 4. So yeah, clearly we see that among these 3 values, so the maximum is 13 by 4, while the minima is 2 by 27. So we conclude that the maximum value of our g theta function is 13 by 4. Okay, so that is why I have written. So the maximum is attained at cos theta is equal to minus half, and accordingly we have the following maximum modulus, right? So this is 2 multiplied by square root of g theta. That is the modulus of fz. So 2 square root of modulus square root of g theta. So g theta is 13 by 4 at cos theta minus half, and that gives us root 13. So yeah, that is our final answer. So inside, so on the given region, so that is the maximum value this function can attain. So yeah, these kinds of problems are quite involved. So like simply you may have thought that you will use the triangle inequality, like mod fz will be definitely less than or equal to mod z cube plus mod z plus 2. So mod fz will be definitely less than or equal to 4 in the given region in question. But what have we seen here? We have seen that the maximum value that is actually attained is root 13. So the value that we obtain from blindly using the triangle inequality is not actually attained here. So this is a subtle point. So even though the maximum modulus is bounded by 4, so that that value is not actually attained in the given region in question. So yeah, so that is why we'll have to go through this detailed analysis. So because you see root 13 is less than 4. Yeah, that's that. So then I'll be going on going to the last problem of this session, and that will be again a maximum modulus problem. So let us begin. So find the maximum modulus of fz equal to cos h ij in the region mod z less than equal to half. So as we know from the lecture, so particularly for this function, the maximum modulus is cos h mod z. So we already know from lecture that the maximum modulus will be cos h of half. But as I said, so we should really go through all these steps. So I will again elaborate the steps. So we already know the answer. The answer will be cos h of half. So let's begin again. So of course cos h ij. So it is an entire function. So definitely it's analytic throughout this region in question. So again by maximum modulus principle, the maximum of modulus of this analytic function must occur somewhere on the boundary, and the boundary is this circle. So this is a circle centered at origin and radius half. So on this circle we will have the maximum of the modulus of this function. So again, so let us parameterize. So since we know from the maximum modulus principle that the maximum will occur on the boundary, so now we will not bother about the interior of the region. We will only think about the circle. So on this circle mod z equal to half, z can be parameterized as z equal to half e to the power I theta. So this is the polar form of complex numbers, and theta runs from 0 to 2 pi. So now again just substitute half e to the power I theta in places of z, and you will get all these terms. So this is straightforward thing. Just so we know that cos h z is e to the power z plus e to the power minus z whole divided by 2. So just put that, express this in e to the power z plus e to the power minus z form, and you will see that this happens. Okay, so I have just written in real plus imaginary part. So, yeah. And its modulus is of course square root of real part, square of real part plus square of imaginary part and square root of this sum. So that is the modulus, and this modulus is obtained as this one. So cos of cos theta plus cos h sin theta. And of course again you will have to go through tedious algebra, and here the functions that will be useful are 5. So these are the two identities that will be useful. So 5 and 6. So cos h square a minus sin h square a is equal to 1. So compare this to cos square a plus sin square equal to 1. So this is the hyperbolic function identity, and these are the half angle formulas. It's like cos h 2a is cos h square a plus sin h square a, and then use this formula 5, and you will easily derive these two identities also. So we'll have to use 5 and 6. And also I guess 3 also, because you see there was these half angles, and yeah, those half angles are multiplied. So there was cos theta by 2, so there is cos theta. So we will also need to use 3, the circular half angle formula. So, okay, so these are the formulas to be used to simplify the modulus into this form. So again, so now we'll have to look for the maximum value of this function, cos theta plus cos h sin theta. So like, and the maximum value of this function will correspond to maxima of the modulus. So again, we'll examine the first derivative. Before that, so something we will now notice that will greatly simplify our analysis. So please note that this property of this function, g theta is equal to g theta plus pi. Okay. So if we put theta plus pi, that gives us minus cos theta, but cos is a even function, so that gives us cos theta, nothing changes. And again, sin theta plus pi gives us minus sin theta, but cos h is a even function, so nothing changes. So if we put theta plus pi here, so nothing changes. So that is why theta, so this is the periodicity property of this g function. So it will suffice only to examine the behavior of this function in this region, 0 to theta to pi. So see, if we know the values of this g function in this region, so we will immediately tell what the values are in the remaining region pi to 2 pi, because of this periodicity property. Okay. So now further we note that g theta is equal to g pi minus theta. So this is another property of this function. Okay. Again, so if we put pi minus theta means minus cos theta, but cos is an even function, so nothing changes. And sin pi minus theta is sin theta, so nothing changes already. So this is another property, g theta is equal to g pi minus theta. So out of this region 0 to theta to pi, so we will only need to look at theta belonging to 0 to pi by 2. So if we just look at values of this function in this small region 0 to pi by 2, we will immediately tell all the values of this function that will be attained in the whole domain 0 to 2 pi. Okay, so now we will focus our attention in this region 0 to pi by 2. Thus again take the first derivative. So this is the first derivative, straightforwardly done. So sin theta. So okay, so there will be 2 minus signs from the first term cancelling each other, and so what do we see? So this is the first derivative, and in the region 0 to pi by 2, you see cos theta is positive. Okay, cos theta is positive. So and cos theta going to 0 to 1 in the region 0 to pi by 2. So we have sine and cos theta. Since cos theta goes to 0 to 1, so sine remains positive. Okay, and sin theta is also positive in theta going to 0 to pi by 2. So in this region, the first term is positive. Okay, and the second term is also positive, because sin theta is positive and sin h is positive when its argument is positive. So and cos theta is also positive. So this is also positive, and okay, and at theta equal to 0, this is 0. So only at theta equal to 0, this first derivative is 0. So as you can simply see by putting theta equal to 0. So we conclude that in this in this given region, so our first derivative is greater than equal to 0. Okay, so this means that g theta is an increasing function in this region. So since it's an increasing function, so of course the maximum will be attained at the maximum value of theta. Like since it's increasing function, so the value of g theta increases from its value at theta equal to 0 to its value at theta equal to pi by 2. So maximum of g theta is at theta equal to pi by 2. And we will now simply put theta equal to pi by 2 and we will get the maximum value to be this one. So let us see. So put theta equal to pi by 2. So cos pi by 2 means 0. So cos 0 means 1 plus cos h, sin pi by 2 means 1 plus cos h1. So 1 plus cos h1, and from our half angle formula, so cos 2a is 2 cos square a minus 1. Okay, so 1 plus cos h1 is 2 cos h square half. So just take this last one here and you will get 1 plus cos h2a is equal to 2 cos h square a. So that is why our maximum value of g theta is 2 cos h square half. So the maximum modulus is cos h half as expected. So 1 by root 2, 2 cos h square half and its square root, and that gives us cos h. So that is our maximum modulus as was expected, and we say that the beginning. So yep. So this concludes today's session. So if there is any question, please feel free to ask.